Hello, everybody. Welcome back to this new week of information retrieval. Hello to those who are on Zoom. Hello to those who are in the lecture hall. So I will start, as I usually do, with a few questions for you on the clicker that you can answer. And then we'll continue. So the menu is, we will continue what we started on the vector space model. So we'll look at the exactly the details of the implementation. I already showed you a little bit, right, how this works with this term at a time, document at a time way of traversing. And we'll see how we can optimize further and how we can, get a bit more performance out of the system to make it work nicely. We'll also look at approximate top K retrieval. And if we even have time, I might start also on the evaluation, performance metrics of the system. And otherwise, anyway, we'll do it next week. All right. So let me switch to the. I need to switch my screen here, and this is my first question. Why is it usually or often not a good idea to use term frequency as a scoring scheme? Right, term frequency is one of those that we've seen, and it's actually not a good idea to just use it alone. All right, answers are coming in. 19. Let's take a look. So we have a majority, and the majority says because some terms may be concentrated in just a few documents. And is that the correct answer? Yes, it is absolutely the correct answer. The rest is just made up. The rank retrieval comes down to Boolean retrieval. The linear algebra is a useless overhead, blah, 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 that's just made up. And the most relevant documents have low term frequencies. We need inverted term frequency instead. No, that doesn't exist. It's inverted document frequency that we looked at. And there are actually people who still, as I showed you last time, there's the flavors for the weights in the vectors, and people who really, really want to use the term frequencies without any inverted document frequency, they can, right? There's a possibility to do it, but it's just often not a good idea. All right, here's another one. This one is what we looked at before. It's this logarithmic merging, right? When we have the indexes and we build, the collection is changing, right? There's documents that keep arriving. And we saw that it's very inefficient if every time we write a new index, or if we keep merging the index in constant intervals, that it's not very efficient. And we had an even better way that's called the LSM trees, so logarithmic merges. And I'm asking to you, among the answers that are on the screen, these are file names, right? I'm just arbitrarily picking one, I0 for the first index, I1 for the double size, I2 for the quadruple size, and so on. And so I'm looking at a specific moment in time, and I look on the disk, okay, what are the files, what are the index files in there? Among these four answers, which ones are permissible? Which ones correspond to something you can actually see as a state of the system on the disk? I0 alone, or I0 and I4, or I0, I2, I3, I4, or I0, I1, I2, I3, I4. Multiple answers possible, if I set it up correctly. So again, you remember it doubles in size, right? You have a first index, and then a second comes in, then you merge it to one bigger index, and then quadruple, octuple, and so on and so on. "13 answers so far. Let me look. It's spread all over the answers. Okay, let me not keep more suspense. All answers are correct, all of them. Remember how it works. It's just counting in base 2, really. You know, counting in base 10 is easy. Well, you're a computer scientist, so you know how to count in base 2, right? But basically what you have is 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, and so on. It's just that it's mirrored, the way you do it, right? You just count, but you mirror the numbers. And every time you add an index, it just increases the base 2 number by 1 if you interpret that as bits that are part of a number. And that means that anything is permissible because, of course, any sequence of zeros and ones corresponds to a number, right? So, all right, all of them are good. Okay. Here's another one. What is the term frequency of term A in document 3? Is it 1, 2, 4, or 11? That should be a quick question. You should not think too much. So let me give you 30 seconds, and I'll do a hard stop at 30 seconds. 19, 20, 9, 8, 7, 6, 3, 2, only 13. Okay, let me. Yeah, so it's 1, right? What's the term frequency of a term in a document? It's just the number of times that it occurs in the document, right? And here it's just once. There's just one A. In document 4, it would be 3. In document 2, it would be 5. And in document 1, it would be 2. Yeah, so the term frequency has 2 subscripts, the term and the document. So it's a matrix if you consider the terms and the documents. And remember that the reason why it's not just 0 or 1 is because we have a bag of word model, not a set of words. So with the bag of word model, we know how many times the terms appear in documents. Okay, here's another one. What's the collection frequency of term A? Again, I give you 30 seconds. Is it 1, 2, 4, or 11? The collection frequency of term A. Right, 5 more seconds. 3, 2, 1, and 0. So it's 11, right? Why 11? Because you just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's just the total number of A's. That's the collection frequency. Is the collection frequency good or bad? Is it useful? Did we use it? Did we not use it? Anybody? Is the inverse of the do we use the collection frequency or the document frequency? The document, yeah. So in fact, we did try the collection frequency. So it was our first try, right? Because that was the first attempt. The problem that we were trying to solve is that if the terms are rare, then the term frequency alone doesn't capture it. And so the collection frequency is the first thing you would think of, right? Okay, let's just try to use it in order to quantify the rarity of a term. And then we noticed that the problem with the collection frequency is that you could have a very frequent word, but it's all in the same document. For example, you have a legal term, and then you will only find it in legal documents. And so you would think, okay, it has a very high collection frequency, so it's not rare, but actually it is because it's just concentrated. So that's the reason why the collection frequency did not completely cover what we wanted. And as a consequence, indeed, we switched over to document frequencies. And here I'm actually directly asking the inverted document frequency of term A. Notice how there's only one subscript, term A. It's not dependent on the document, right? Please use the log in base 2 to not overcomplicate things. So what is the inverted document frequency? of term A here. So first, you need to remember the formula, right? So first, you need to remember what the document frequency is. And then you need to remember the formula in order to derive the inverted document frequency from the document frequency. Or you could also notice something that directly gives you the answer. Right answers. Okay, let me first display the answers. So we have many zeros. Some say 3. Okay, so first, what is the document frequency? You can also write in the Zoom chat, right? We are looking also in the Zoom chat. Abhishek is here with me. So what is the document frequency? If you don't compute the inverted one, what is it? Yes? Yeah, exactly, and that is 4 times, exactly. So indeed, it's the number of documents that contain terms A, and that's 4. All right. And then if we compute the inverted document frequency, what is the formula? Yes? Yeah, and that gives us 0, exactly. So the inverted document frequency is logarithm of the number of documents, that's 4, divided by the document frequency, that's 4. So the logarithm of 1, and that's 0. So this is why the answer is 0. But in fact, you could also just notice that the term A is everywhere, right? It's basically a stop word. It occurs everywhere. And the 0 is the bare minimum an inverted document frequency can have. And this is where it's everywhere. That's another way of telling. Okay, do we have in the chat a remark?
Question. Could you please explain again why we use the logarithm for inverted document frequency?
Yes, that's a good question. So indeed, we could also just have used the inverse, right? N over the document frequency. I think it has to do with smoothing a little bit, because if you don't use a log, then going from 1 to 10, and then 10 to 20, and then 20 to 30, you know, it makes a big difference every time. But at some point, if you have, let's say, 1,000 or 2,000 or 3,000, it shouldn't really matter anymore. So the logarithm is a way of smoothing that scale, of basically looking at the order of magnitude rather than the actual the actual inverse. So this is, I think, the main motivation. But the question is totally legitimate because it's not obvious. And in fact, this is the reason why we saw that there are alternative ways of using the weight, right? So the IDF, the inverted document frequency, is one of them, and there's others. There's other ways. Does it answer your question about the log?
Yes.
Yeah. All right. Perfect. Thank you very much. Yes. There's another question. Maybe the microphone. Yeah.
I initially thought that the intention was to bring it down to 0. Basically, what we say, the rarity is 0, so it's not there at all.
That is also, yeah, that is also a good point, indeed. So there is the effect of the scale, and there is also indeed the effect that it recalibrates the bare minimum to 0, as opposed to that would have been n, basically. So no, n over, I think n over n, that would have been 1. Yeah, exactly. So I think you're right too. It's a good thing to have 0 as the bare minimum. Yeah. In fact, this is what I would almost call, you know, mathematical cooking. You know, when you're a mathematician, you're also a cook, and you just need to cook your formula in a way that you make it do what you want it to do. So yeah. All right, let me just stop here with questions. Maybe I'll ask a few more later, and let's go back to the continuation of the lecture now, but I hope it was a good way to refresh what we have seen previously. All right, so let me reproject the slides. Then I hope that this works. No, it doesn't. Let me just, I think I might need to start this Logitech presentation. I'm not sure why sometimes it just started to fail me completely, and I have absolutely no idea why that that the Logitech presentation just stops working. Otherwise, I'll just press keys on the keyboard, just less convenient, but yeah. All right. Okay, so what have we seen? What have we seen so far? So we've seen that in Boolean retrieval, we have a query with, sorry, I'm supposed to show here. We have a query with and or not and so on. And then we extract a subset of the documents from the overall source of documents, right? And in ranked retrieval, what we have seen last time, instead of having a subset, we have a ranked subset. So this is the first, this is the top output, then the second, the third, and so on. So this is how it feels on a search engine on the web, right? And we also looked at parametric search, which is what happens if in libraries, especially if you look specifically for title, author, and so on and so on. And we saw that in that case, we have an index. It's pretty much relational databases, right? We can build indices on each one of the fields that we have in here. We can build an inverted index, again, that has the zones in there. So in addition to the postings, you have also that it's in the title, in abstract, and so on and so on. And we saw that we are able to have a scoring system by computing the dot products between a matrix of weights that is right there. G has some weights, and S is 0 or 1, depending if it belongs or not, right? And in that way, we are able to aggregate a score. The more it appears, the higher the score, right? So this was our first attempt at ranked retrieval. We saw that you can use machine learning if you want to find out what the best values of G are. This is basically a machine learning problem, and you just learn, it's the parameters of your model, and then you just learn these parameters, right? And this is machine learning stuff, right? Minimizing the loss and so on and so on. And this is covered in other lectures, like Introduction to Machine Learning. Then we saw that's an even better attempt that we can look at the term frequency. As I told you, it's a matrix. There's two subscripts, the term and the documents, and you have one value for each. The inverted document frequency, that is 1 per term, right? And if we multiply them together like this, that's called the TF-IDF, term frequency times inverted document frequency. That gives us the weights of a vector, right? You can consider a document as a vector that has the TF-IDFs for each term, all right? Then we saw that we thus come from a level of abstraction where we had vectors of Booleans to now vectors of numbers, because we have the TF-IDFs in there, right? So this is what happens. And we have bags of words, no longer sets of words. As a consequence, since we have vectors with numbers, we are in a vector space. Of course, it's not a vector space with just 2 dimensions like here. It's plenty of dimensions, like a million dimensions, but it's still a vector space. Since the vectors, the values are positive, it's the first quadrant. So it's only that part of the system, and there's nobody here, just the first quadrant. So we saw that each document is just a point in there. And then we can compute the proximity between 2 documents. What do we use? What operation do we use to do that? Anybody remembers? Yes? The dot product, exactly. If we compute the dot product, so you see the dot product is basically very high if they are almost linear, and it's 0 if it's perpendicular, right? So this is very high, very low. So as a consequence, the dot product gives us a measure of that proximity. And since the query itself is also a vector, it's also text, then we can compute the dot product between the query and the document. So we just want to find the documents that have the highest possible value of the dot product with the query. So it means that we just basically need to compute the dot product, right? So now we are done with the math, and we have a computer science problem. And the computer science problem is, how do we compute the dot product? So the way a dot product is computed, remember, it's the sum of the pairwise product of the coordinates. A sum is easy. This is just a for loop, right? You just keep iterating, and then we need to compute the terms of that sum. Term in the mathematical sense, the terms of a sum, the factors of a product, right? So this is one term of the sum we want to compute. And notice what's happening here. There are two big parameters here. There is the term and the document, right? So term is coming from here, and there is the document that is basically D. The sum is over the terms. So it's a sum over T of these things, but it's parameterized by D, that is kind of the external, it's a constant with respect to the sum, right? So for every D, we need to sum that over T. And we saw that there are two ways of basically doing that. There is the term at a time, where we just pick a term and compute all the now it's funny to say pick a term and then compute the terms, because it's using term in two different ways, but I'm sure you understand what I'm saying, right? You just pick a term, compute that for every document, then go to the next term, and so on and so on. And then what you do is you accumulate these values every time in the right bucket, depending on D, right? And you sum over T in every bucket. All right. Then we saw that there is this notation called SMART. Why is it called SMART? I actually didn't tell you that. SMART was one of the very first systems that was built, I think it was in Cornell University, a very long time ago, decades ago. They invented basically the vector space model. They invented also some what is called relevance feedback. I'll tell you a few words about that. And they also, as part of the vector space model, invented that system that is a notation system to basically tell how the weights are invented. And this is why we have these 6 letters, where we have the documents on the left and the query on the right. And then we have here how we compute the term frequency, the document frequency part, and the renormalization part. And with the letters, you know exactly how you fill in the weights of your vectors in the model. Right, so this is called the SMART notation. It's, even though the SMART system now, I don't think it's as a software it's used anymore, but there is a bit of legacy of that system, and this notation basically is what we have preserved from the system. All right, now, in order to do it efficiently, we can simplify a few things, right? So we have the product of the TF-IDFs and renormalized with the norms of the vectors. So of course, this is one specific SMART notation, right? Of course, if you change the SMART notation, then you get different things, right? But I'm using the one that we often use with TF-IDFs and the Euclidean norm, right? So I explained to you that you cannot really put doubles in there because they are hard to compress. We saw that we can compress integers. We did it in the index compression part. So this is why we don't put the TF-IDF here. Rather, we only store the term frequency here and the IDF part there, possibly not taking the log, but just the inverse, and we take the log dynamically, right? So this is it. So you see where everything comes from, right, in order to compute that. Now, there's a few things you can simplify. First, the query length is totally useless. It's totally useless to renormalize by the query. Why? The query is a constant. It's the same for every document. It's the same for every term. So you don't care. You're just comparing scores, right? So if you divide all the scores by the same number, it doesn't change the ranking. So that's great. We can get rid of it. There you go. It's gone. Next, the division by the document length. Well, it doesn't depend on the term, right? So you don't need to divide for every term. So you can keep it to the end to divide by the document length. You still need to do it for each bucket. So each bucket here, each document has a different length, but you can do it at the end, right? So now all you need to accumulate is the product of the TF-IDFs. Next, you don't need accumulators for documents that don't contain any terms of the query, right? So you can throw away a few of these buckets right there, right? So there you go. So you see, we can do quite a few simplifications in there. And many of the queries also we can add have only 0 or 1 in the weights. Why? Because if you think of writing a query, it's quite rare that you repeat a term. Why would you repeat a term in a query? right? You just write the terms you're looking for. But there is, of course, use cases. You could always find a counter example, right? And for example, if you're experiencing a bug while coding with Python or Java, and you copy paste the error message in a search engine, of course, you're going to have repeated terms, right? But in general, if you do a natural search, you'll rarely repeated terms. So that means that we don't care about the term frequency on the query side. We can drop it. So it's basically changing the smart notation here, and we can drop it. We can just drop the TF part on the query side. So you see it's simplifying a lot. Now we see it's twice the same thing, right? The inverted document frequency on the term doesn't depend on the query. So we can actually throw away one of the two. That also has to do with the smart notation. So we basically drop the term frequency. We don't renormalize, and on top of that, we throw away the IDF. So I think what we get is NNN or something like that on the query side if we do that, right? All right, so you see it's much simpler, right? So now we just have to sum the TF IDFs over the documents. All right. So is it clear for everybody how this works, right? We reuse the standard inverted index that we have already designed. We've already designed that at the very beginning of the lecture. We augment it with term frequencies and convert these document frequencies to inverted document frequencies. And now we traverse it, accumulate the TFs and DFs in the buckets, one for each document. And at the end, we have the scores and we rank. And we can rank in linear time as opposed to n log n, because we use a heap structure and we only pick the top 10 or the top k documents. And speaking of the top k, there is an optimization that we can actually do. Because at first, you would think that we have to do this computation of the scores for an enormous number of documents, right? So we eliminated those that don't have the terms, but it can still be a lot of documents. If you're thinking, for example, of a search over the internet, over the web. So that might still be a lot to compute. And what if we could just throw away some of the documents early in order to restrict the set of documents for which we actually do these computations? And the idea is that this happens, this problem, that if we have very large postings lists, then that gives us a lot of buckets to compute. So what we do is we reformulate the problem mathematically, are finding the top 10 in a very large set. Instead of the very large set, we pre-select some of the documents that we think are good candidates. And then we only compute within that set of pre-selected documents, we are going to compute the scores and find a top 10. But it's going to be an inexact top 10 because that's a top 10 in a smaller set. And of course, it has consequences. We might miss documents. Maybe there were documents that are relevant outside of this pre-selected set. It's a cost. It's a price to pay. We're missing them. And we have an inexact top K retrieval. In many cases, people are happy about that. All right. So let me ask you a question. Why do you think inexact top K retrieval actually makes sense, and that it's actually this price to pay, that we might be missing good documents? Why is it actually not so bad? Because it's only an approximation, right, of the top 10 in the entire set. Do you have an argument that would justify doing that? And after all, it's not such a high cost, or it's not such a big issue. On Zoom, anybody? Do you want me to tell you? Okay, let me tell you then. So remember that we have this vector space model with the dot products that compute the scores. But who said that computing the scores in this way with the dot product of the TF-EDF, who says this is reality? It's not reality. This is already an approximation of reality. This whole thing with the dot products and the TF-IDFs is a mathematical trick that we have to compute scores. But there is nobody who says that this is the only way to compute scores. So the argument goes, it's already an approximation of reality to compute the dot products on IDFs. the ranking you get, it's not an absolute reality. It's one way to get the ranking. So if you take an approximation of reality, it's not so much worse than just an approximation of reality, right? So this is the idea. So this whole scheme about the dot product of TF-IDF should not be taken as something immutable or that is perfect and absolute. It's already an approximation. All right. So let's try to do a few more tricks in order to eliminate basically these documents and simplify the whole thing. So I have this query. I just picked the 4 terms that I have in there: ETH Zurich and school, and I have ETH Zurich and school, and these are my posting lists that I have in there, right? So now I will use a bit of visuals here. Instead of putting numbers, I will just use I just vary the height of the rectangles there, right? So, for example, you might have noticed that end is a stop word. So the IDF is going to be very low because the DF is very high. So the IDF is very low. And the same goes for school. It's more frequent than ETH Zurich, right? So what you can do is you can say, let's get rid of these 2 here that has a very low IDF. Let's not even bother computing the TF IDFs or accumulating them. Let's stick to just these 2, right? And the idea is that the reason why there is a very low IDF here is that it's a very large posting list. In fact, we are just eliminating, what is it called? When there's a lot of postings, it's a stop word, right? So it just comes down to eliminating stop words if you do that. Right. All right, so that's the first idea, that you eliminate the index. And what happened in there is that we dropped a lot of documents that were in end and school, that contain the terms end and school, that might not appear at all in ETH Zurich. Is that a problem? I don't think so. If you type ETH Zurich and school, you probably don't care about the documents that have neither ETH nor Zurich, right? So this is why the inexact top K actually kind of makes sense. So you focus on the non-stop words. All right, there's a second idea, another thing that you can do. The idea is that you can keep the documents that contain many of the terms. So for example, you could have a document that contains all 4 terms in here, as opposed to a document that only contains Zurich and not ETH. So what you could do is you keep the documents that contain all terms and you drop the documents that only contain one of them. Maybe you can have a threshold or something, right? This is something you can figure out with the intersection algorithm, right? To find the documents. You could, for example, if you want to put the threshold at the maximum, you just compute the intersection of all 4 posting lists, right? And that gives you the documents that have all 4 terms. It's kind of the Boolean retrieval, right? You take the end literally. All right. The problem is you might be eliminating too many documents because maybe 3 terms would already have been enough. And you don't care, for example, if there's not school, but there's ETH and Zurich, maybe you're fine with that. Right, so maybe you can set the threshold a bit lower than 4. All right. Okay, but there is another trick that, as you can imagine, is being decays, right? So yes.
Come back to the stop words. Stop words is part of the language processing. Are you saying that if we aim for the vector space model, we don't do this part? Or?
So it's all orthogonal to each other, right? You could have done the elimination of the stop words before, or you could do it at that point. The point that I'm making when I'm saying this is equivalent to eliminating stop words, it's more of a conceptual remark that if you haven't done it before and you do that, then it's kind of doing it anyway, right? So I'm just saying that you're coming at the same thing from 2 different perspectives. From the perspective of the stop words at language preprocessing time, or from the perspective of inexact top K retrieval later. I'm basically just crossing ideas here. I'm just saying and I will do it again many times to say, okay, we just land back on the same idea from a different angle, right? Does it make sense? Okay, awesome. So now let me tell you here these tricks. So let's change the sorting of these posting lists here. They are sorted by increasing posting ID. Let's sort them by decreasing term frequency, right? So I'm starting with the documents that have a lot of occurrences of my term, and then less and less and less and less. So again, I'm using the visuals that the height of the rectangles here is basically the term frequency. All right. So if we sort by decreasing term frequency, we can cut into and only keep the top K documents, only select the, the left part. We can put some R, some arbitrary value R, and then we just look at the top R documents for each term, right? Again, that's assuming we sorted the documents by term frequency, by decreasing term frequency. Otherwise, we cannot do it so easily, right? So we just compute the union of the top R for each term, the top R documents, and that gives us an inexact top K as well. We don't have all documents, but we just have those that have the most occurrences of our terms, right? And R is something you can choose statically. That means before you even receive the query, right? When you build the index. All right, but you can also, one way, choose statically. Another way is to make R dependent on the IDF, meaning that if the term is rare, it has a very high IDF, then you pick a larger R to pick more documents. And if the IDF is low, you can pick a lower R. And then you're back to the idea of the stop words, if you do that, right? That you can pick R that even becomes 0 for the stop words, and that's equivalent. All right. Now, can anybody tell me what's the difficulty if we do that? So I sorted my documents by decreasing term frequency. I'm only considering the part that is in the rectangle here, and I'm throwing away everything on the right. And I want to compute the union. Why do I have a problem? On Zoom? Nobody on Zoom. Do you remember the union algorithm, how it works? Why will we not be able to use the union algorithm here? Yes? Exactly, or they're not sorted. Exactly, there is no common sorting. That's the problem. They are not sorted in the same order on the both sides. You're exactly right. That's exactly the idea. So when we sort by posting ID, by document ID, the documents are always in the same order for all terms, right? If you have document 2 and document 4, document 2 will be before document 4, whatever the term. But here, this order of the documents depends on the term. It might be that document 2 is before document 4 for ETH, but document 4 is before document 2 for Zurich. That means that your union algorithm breaks. It doesn't work anymore because the union algorithm is assuming that there is a common order, right? That you just traverse. It's basically the merge sort algorithm that you do here. But in the merge sort algorithm, you assume you have the same order throughout the algorithm, right? So we have the problem that we cannot simply use the union algorithm if the documents here are sorted according a different criterion for every term. Yeah, all right. And that's, I put it again, because the order of the documents depends on the term. So what you can do to fix that, oh, if I push that down, that's not gonna help. In order to fix that, you can just come back on your decision and not sort the documents by term frequency. You keep the original order. You keep sorting them by document IDs. So then the union algorithm is going to work. And what you do is you use this sort by term frequency and selecting the top R, but you only use it in order to build a separate list. Right there. So you build the champions list. That's called the champions list, what we did with the top R by decreasing term frequency. We just build them separately, right? And then we have this separate list, and we just run the union algorithm on this separate list. Of course, there are plenty of variations, right? Because what's important is that you don't get the impression that there is one way of doing that. There is not one way. There's many, many, many ways of doing that. What you need to understand is all the ways that you can do it and recognize what's a good idea, what's less a good idea, so that you can adapt, right? So it's like a big toolbox with plenty of ways that you can improve things. Okay, here's another one that's called the quality score. A quality score, an example is PageRank, if you want. PageRank is Google's algorithm for web pages. It assigns a number for every web page. It's something that tells us if a document is a good document or not a good document. And you want to prioritize the good documents that you give back to the user. So you could assign to every document a quality score. And then you can sort statically the documents by quality score. Can we apply the union algorithm? Who thinks yes, we can? Who thinks no, we can't? Also on Zoom, you can, let me look at the hands. Let me do it again, this time with Zoom. Who says we can use the union algorithm if we sort the documents everywhere by their score, quality score? The yes, we can. Okay, and on Zoom, I don't see any raised hand on Zoom. Oh, I see a green tick and a red tick. Oh, that's a feature of Zoom that I didn't know. Yeah, interesting. Okay, and now the no, we can't. Who says no, we can't? Okay, some of you. And on Zoom, here we see the, so majority says no, we can't. In fact, we can. Let me explain why. The reason we couldn't use it before was that there was no common order, right? Because the term frequency depends on the term, the order. But in that case, that score, that quality score of the document, it's independent on the term, right? The page rank doesn't depend on the word on a page, it's just a page rank. And it's because the quality score does not depend on the term that we can use the static quality score as an alternate way of sorting the documents instead of the document IDs, right? All right. So what we can do, so you see all the flavors of what we can do. We can use the static score to sort the documents, and we can tweak this term frequency order a little bit, adding the static quality score right there to the TF-IDF. That's yet another way of doing that. However, this depends on the term. So you cannot use it to sort the documents for your union algorithm, but you can use this to find the top R for the inexact selection, right? So you could use this instead of the decreasing term frequency, right? So you see, I've basically showed you maybe 10 ways or 10 tricks that you can use in order to improve your system. And then it's up to you when you actually do or build the system in the end, how you do it, right? Okay, so here we can sort everything by the static document frequency. And the highest term frequencies, there might be not exactly all at the same place. But you can separate the lists with this top R, having a first list where you have the top term frequencies, and a second list that's called the low list. So there's the high list and the low list. And what you do is that you start with the documents that are in the top R. And if you don't have enough results, if you didn't get enough to display to the end user, then you start querying the low list. All right? So a higher way of looking at it, or higher level, if we zoom out, is that we have the entire standard inverted index. We sort by decreasing IDF, the very frequent terms to the not frequent term. We sort the documents here by, so in that case, I think it's by TF-IDFs. And we can traverse, what do I want to say here? Yes, we start here and we go like this in terms of the looking for documents. Okay, let me just, forget the last 20 seconds of what I said. And after the break, I'll take it from there and explain what's going on right here. Right. So I'll see you in 15 minutes to continue the lecture.